Hello, Duhawks. Thanks for tuning in. We are continuing our conversation as it relates to energy expenditure. And so, thus far, we have talked about the energy systems as well as the mechanisms for which we utilize energy. And next, we're going to take a look at maybe. Next, we're going to take a look at the ways in which we can measure energy expenditure. Okay. So we ended here last time talking about average amount of calories that we could burn in 1 hour. Again, these are just simply some examples. However, it's important for us to note that as intensity increases, the amount of calories that we're burning per hour will also increase linearly as it relates. So let's take a look at how we can measure energy expenditure. Okay. So there's really two different methods that we could utilize. We can use direct calorimetry and indirect calorimetry. So direct calorimetry works off of this concept that basically 40% of the energy that we liberate during the metabolic pathways is used to produce or create ATP, and the other 60% is released as heat. Okay. Again, when we think about using a large amount of energy, such as during exercise, right? That's why we sweat, because we are producing a large amount of heat in order to do so. Okay. So therefore, one way for us to measure energy usage is to look at the amount of body heat that we're producing at any given time. And that process, again, is known as direct calorimetry. Okay, so with direct calorimetry, notice that we've got this lady in this enclosed chamber. And essentially what we're going to do is we're going to have tubes of water surrounding the edge of the chamber, and we're going to look to see how that water is warmed as it travels around the outside of this chamber. Okay, so it's basically a process through which we're going to measure temperature change seen in this fluid as it moves around the surrounding, edges of the chamber. Okay. Issues with this particular method of measuring calorie expenditure: it's very expensive. It's very slow to measure. Also, notice that this chick, it looks like she's got like a skirt on, running on a treadmill. Whatever, to each their own. It is also important to note that the treadmill, because the treadmill is a machine, will also produce heat. So the treadmill will give off some of its own heat. Also, it's important to note that not all heat is liberated. So some of the heat that we produce will be stored in the body, which is why our body temperature increases during exercise. So again, direct calorimetry was kind of like our first way to determine how many calories we're actually expending. However, there are many negative, I guess, issues associated with using this method. Okay. A better method is known as indirect calorimetry, and you can see that here in this picture. And basically what we're doing with indirect calorimetry is we're looking at the amount of oxygen that we're utilizing and the amount of CO2 that we are producing in order for us to estimate our metabolic rate. Okay, so again, we get a really good idea of the total number of calories that we are expending from an aerobic standpoint by understanding how much oxygen we're actually using. Okay, so again, keep in mind that that's separate from how much oxygen or air I'm breathing in. It has to do with how much oxygen I can move from my lungs into the blood, and from the blood to the tissues, and then in the tissues to actually be used, right? So a small percentage of what we bring in is actually being used. So that's our ability to measure oxygen consumption. And then we can also get a good idea of what types of fuels we're using based on how much waste product we're producing, the CO2 production. Okay. One con associated with using this method: it doesn't account for anaerobic activity, right? So again, if the major method that we're looking at here is how much oxygen we're consuming, it doesn't allow us to account for how much work we're doing from an anaerobic standpoint. Additionally, it can give us ideas about where we're getting this energy from, right? So are we using carbohydrates? Are we using fats? Are we using proteins? Okay. So Again, as mentioned, for aerobic metabolism, we can measure our oxygen consumption through VO2. And again, VO2 tells us how much oxygen we're using and hence how much fuel we're utilizing from an aerobic standpoint, okay? However, it doesn't tell us what our fuel source is. So simply by looking at VO2 or the amount of oxygen we consume, we know how many calories we're using, but it doesn't give us any information about what fuel. Okay, so that information is coming up here soon. Again, it also does not account for anaerobic fuel contribution. So at high intensities, this is not super accurate because we can only really estimate how many calories we are expending from an anaerobic standpoint. Okay. We can determine which fuels we're using, whether that be fats or carbohydrates, based on this measurement known as RER. Okay. RER is known as a respiratory exchange ratio. Sometimes it's also called, let me write, sometimes it's just R as well, or sometimes it's called RQ, respiratory quotient. Okay, so RER, R, and RQ are the same thing. So if you see those somewhere else, or maybe you've heard of those in different contexts, they all mean the same thing. And basically what we're looking at here is the amount of CO2 that I've produced in comparison to the amount of oxygen that I'm utilizing, okay? And it's able to tell us what contribution we're getting from which fuel source, okay? So if we're using fats, our RER value will be something like 0.7. If we're using carbs, our RER value will be something like 1.0. Okay. So again, that's kind of the range for us to be able to apply this principle. So again, an RER of 0.7 would indicate that we're using fats as a fuel source. An RER of 1.0 would indicate that we're using carbohydrates as a fuel source. We can also have an RER value of like 1.2, for example. Okay. So again, if I know that 1.0 gives me carbs and 1.2 is available to have happened, let's take a look at those components again. So that tells me that my waste, my CO2, is greater than my oxygen consumption. Okay. So if I'm above 1.0 for this ratio, that means that the waste that I'm producing is more than the oxygen that I am consuming, right? So what this tells us, above 1.0, tells us that there is an anaerobic contribution of some sort, okay? So anything above 1.0 tells us that there's anaerobic contribution. Also, we know that when we work at high intensity, that means above 1.0 also is relying on carbs. Okay, so we're 100% relying on carbohydrates at 1.0 or higher. Okay, 1.2 is probably about as high as you could go. We might see a 1.3, something like that, somewhere along the lines, but 1.2 is pretty darn high. Okay, again, let's say I was, and again, if 0.7 is fats and 1.0 is carbs, what if I have a 0.85 or something like that? Well, that tells me I'm using a mixture. I'm using both carbohydrates and fats in order to produce those calories, okay? Another thing that's important to note with RER is that we're assuming about proteins are contributing 15% of our total energy expenditure. Okay, so proteins account for 15%. If I'm at 0.7, the rest of it pretty much is fats. If I'm at 1.0, again, I get 15% from proteins and the rest from carbs. Okay. Again, we've alluded to this idea that we haven't accounted for anabolic or anaerobic measurements at all. So we think about anaerobic contribution to energy expenditure, it's much less accurate. Okay, so a universal measure doesn't exist for us as it relates to measuring energy expenditure from an anaerobic standpoint. Okay, some things that we could use in order for us to get a better understanding of anaerobic energy contribution, we can look at oxygen debt And oxygen debt, again, would be similar to that EPOC that we talked about. So with EPOC or oxygen debt, I'm able to understand how much oxygen I need in order to make up for what I did during that particular exercise bout. I could also look at blood lactate values, which allows me to understand from an anaerobic standpoint what's the contribution of that anaerobic glycolytic system. I could also use power output, so I could use wattage from my ergometric test. So again, I can use watts on a cycling test, for example, in order for me to kind of standardize and understand what's the anaerobic contribution that way. The most painful thing that we could do would be a muscle biopsy for creatine. Again, if you remember back to that first energy system that we talked about, the ATP phosphocreatine system, creatine is kind of a waste product because we pull off that phosphate from that molecule in order for us to regenerate ATP. So I could go into the muscle and look to see how much creatine I have left after an exercise bout, and that would give me some information about how much phosphate I used from those creatine molecules. However, that's not a common method because a muscle biopsy is fairly time consuming, like in terms of being able to go in there and get that. And basically what they do is they take like this thick needle and they're gonna like shove it through the middle of your muscle belly and pull out a chunk of muscle, like a little sample of your muscle, to be able to then look at that and see what's going on in there. Super painful, number one, and causes a fair amount of muscle damage. So again, if I'm somebody that's considering being a subject, like I don't really want to have some muscle damage going on in order to check to see how much creatine is within my muscles. So muscle biopsy not commonly used in this particular example. Okay. So we talked about the possibility of using carbohydrates and using fats for metabolic purposes. But how do we regulate this during exercise? Okay, so again, we said with high intensity exercise, I'm going to rely on carbohydrates. During low intensity exercise and at rest, fats are more important for me in regards to, supplying energy. Both carbs and fats are responsible for maintaining those muscle ATP levels during prolonged exercise. So again, if I'm doing anything greater than, let's say 60 minutes, I'm using both energy sources for sure. Okay, so various hormones are going to work together to ensure both glucose and fatty acids are available for energy metabolism in those given situations. So you might have seen this before. This is known as the crossover effect. So here you can see the relationship between intensity and energy contribution. Okay, so we know that with an increase in intensity, the total number of calories that we are expending will increase. However, it's also important for us to look at substrate. Okay, so which fuels am I using in which scenarios? So at rest or during low intensity exercise, notice that carbohydrates are contributing, 15%, whereas fats are maybe contributing 85%. Okay. As intensity increases, we reach this moderate intensity where we have this crossover where it's about 50-50. So carbohydrates are contributing about 50% and fats are contributing about 50%. Again, as we increase exercise intensity, we know that at the highest intensities, we're exclusively relying on carbohydrates, so 100%, and 0% contribution coming from fats. Okay. Again, when we think about how this applies to real life, knowing these things is super important in terms of allowing us to determine what our nutrition should be like, right? If I want to be a high intensity athlete and I want to compete at a high intensity, then I need to freaking fuel myself with carbohydrates, get the fats out of my diet, right? We don't want to be consuming a large amount of fats because they're not able to help us in this particular scenario. Okay. If I'm doing something moderate or prolonged in nature, then having healthy fats in the diet would be good, would be fine, right? This shows you the relationship between substrate choice and duration of exercise, okay? So again, we mentioned that during prolonged exercise, we will start to rely more heavily on fats as a fuel versus carbohydrates, okay? So here you can see muscle glycogen levels. So again, glycogen is your storage form of sugars or of carbohydrates. Okay, so muscle glycogen will serve as our primary source of fuel. Again, here you can see like, I don't know, that's probably like 30 minutes or so in duration. 40 minutes, 50 minutes, something along those lines. Notice that it takes a long time to get those fats activated. Okay, so fats aren't even contributing to the situation until about 60 minutes in. Okay, so I have to exercise greater than 60 minutes if I plan to utilize fats as a fuel source. Notice that as that exercise duration continues, the reliance on fats will increase substantially, while glycogen levels will play less of a role. Okay. So again, this crossover effect here shows us the relationship between fat metabolism and glycogen usage as it relates to duration. Okay, so I have to do at least 60 minutes of exercise in order for me to even tap into my fat fuel sources. Okay. This shows us what percentage of glycogen we're able to utilize. Okay, so during light exercise, again, I have a limited supply. I have a limited supply of glycogen. Okay, so you know, when I'm doing light exercise, I'm really not burning a whole lot of that, right? So I'm able to maintain those glycogen levels. I've got about 2,000 calories stored of glycogen. Okay, as I begin to participate in moderate intensity exercise, okay, if I do, I don't know, 60 minutes of moderate intensity exercise, I use like half of my glycogen. Okay, if I'm doing 2 hours of moderate intensity exercise, notice that I've used almost all of my muscle glycogen. Okay, heavy exercise, so high intensity exercise, I can deplete my glycogen in like 1 hour, basically. Okay, again, I would emphasize to you that this tells us the importance of nutrition as it relates to fueling ourselves for exercise, right? If I'm going to do moderate but prolonged exercise, or I'm going to do heavy exercise for up to 60 minutes, I need to fuel myself appropriately with good carbohydrates in order to make sure we are topping off these glycogen levels so that it doesn't limit our ability to complete that exercise task. Okay. Again, you know, we mentioned that sugar or glycogen or glucose is a very important fuel source for us during high intensity exercise. Okay. Glucose will serve as our exclusive fuel source during high intensity exercise. Okay, so heightened energy demands require more glucose to be available within the muscle cells. So how do we do that? How do we get sugars available and ready to go as I am exercising at this high level? How do I get those fuels available? Okay, so how do we increase glucose levels or increase these sugar levels within the muscles so that we can work at a high intensity? Okay. Glucose metabolism is related to our ability to get those sugar molecules from their storage form into a more basic form that we can use. Okay, so I want to take the glycogen, which again, if glycogen is my storage form, imagine that it's like this long strand and I've got like a bunch of little beads on here. Okay, so again, like the strand of bead, and each one of these little beads is a glucose molecule. Okay, long strand is the glycogen, the storage form of this. Okay, so in order for me to get those sugars out, I need to do a process known as glycogenolysis. Okay, genesis means to create, and then glycogen, again, we're looking at sugars. So again, we're basically nipping off those glucose molecules. So glycogenolysis is the process by which I take a glycogen molecule and I break it down so that I have a bunch of glucose molecules. 5 hormones are going to be important for this process to occur. Epinephrine, norepinephrine, glucagon, cortisol, and growth hormone. And again, I think I show an image of these maybe on the next slide. So let's take a look. Not this slide, maybe the next slide. Okay. So again, those hormones were epinephrine, norepinephrine, glucagon, cortisol, and growth hormone. Okay. So again, when we think about our ability to utilize glucose or utilize sugars, our plasma glucose levels during exercise are dependent on really two things, okay? Supply and demand, essentially. Glucose uptake into the exercising muscle. So again, the more work that I'm doing, the more glucose I'm uptaking into that muscle that I'm using, okay? And then secondly is our supply, okay? So glucose release from the liver. So how fast can I get through glycogenolysis? How quickly can I take those little beads off of the glycogen strand and release those into the blood so that they're ready to be used? Okay, so again, let me say that again. The plasma glucose levels during exercise are dependent on supply and demand. Okay, so how fast am I using sugar? How fast am I burning through it? And how quickly am I getting sugars out of storage? Okay, how fast am I using the sugar has to do with glucose uptake at the exercising muscle. And my supply has to do with glycogenolysis. So how quickly can I take that glycogen molecule and break it down into simple chain glucose molecules that are released into the blood? Okay. Again, as mentioned on the previous slide, during exercise, we're going to increase the release of these hormones: glucagon, epinephrine, norepinephrine, cortisol, and growth hormone was the other hormone that's not mentioned here, but also would play a role. Okay, check this out. So these hormones are supposed to assist us in being able to increase glucose levels in the blood. And guess what? The longer I exercise, the higher these hormones get. Okay, so the more I exercise, here we're looking at duration. Okay, so the longer time-wise I exercise, the greater the release of these hormones. Okay. Notice the inverse relationship that we see with the hormone known as insulin. Okay, so let's think about the difference between insulin and glucagon, for example. Those two hormones are considered opposites. Okay, so insulin is released when I eat a meal. Okay, and insulin's job is to help us to store sugars. Okay, so let's say I go upstairs and I'm going to have, what am I going to have for lunch? I'm going to have some mangoes. I got some mangoes up there, and I'm going to have wrap. Okay, so again, all of those sugars that I'm consuming with like the fruit and the wrap or whatever, okay, I'm going to release an equivalent amount of insulin so that I can help to store those sugars. Okay, so insulin's job is to help store sugars. I don't want to be storing anything when I'm doing exercise. Okay, so during prolonged exercise, we're going to see a decrease in insulin. Okay, however, glucagon will increase. Okay, so glucagon's job is to do the opposite of insulin. If insulin's job is to help store sugars, glucagon's job is to help get sugars out of storage. Okay, so the time between the meals. Okay, so let's say I eat that lunch and then I'm not going to have anything. It's like 11:20 now. Okay, let's say I'm not going to have anything else until probably like 4 today. Okay, so again, I'm going to burn through those calories pretty darn quick. So I'm going to have to rely on glucagon a little bit later in order for me to release more sugars into my blood so that I can maintain my, sugar levels. Okay. So again, that's just normal life. Imagine a scenario where I'm burning a lot more calories than just at rest, right? So during exercise, we need to increase these hormone levels substantially, and we do. So that's real neat. That's good. Okay. So another thing that's important for us to note is this relationship between glucose and its ability to enter into a cell. Okay. So again, this is a scenario where I wish I was a good artist, which I'm not. That's my bloodstream. And there's a cell. Okay. So again, when we think about insulin, okay, I ate the mangoes and the wrap, and now I got a bunch of little sugars floating around in my blood. Okay. I digested those foods, I broke them down, now there's sugars floating in my blood. Okay. Now, insulin's job is to come over to this cell and open a door, which is known as a GLUT1 transporter. It's a special little door, and that's going to allow those sugar molecules to come into this cell, okay? So that I can like store those sugars that I just ate for lunch, okay? However, we said during exercise, insulin, he gone. So I don't have that, okay? Well, how am I going to get sugars inside of that cell? I'm going to use a different door known as a GLUT4 transporter, okay? So the GLUT4 door, think of him as like, he's like the side door here. He's going to allow those sugars to come in even though insulin is not there, okay? So GLUT4 will allow us to uptake sugars without insulin available, okay? Which is what we're going to do during exercise. GLUT1, which is what I showed you over here, is only activated when insulin is available. So this is like the front door to get into the cell, okay? So insulin has to unlock this door. Well, the side door, GLUT4, is already open, okay, if I do exercise. So I don't need a key to get in this way, okay? So cool thing with this, when we think about GLUT4, I can upregulate this just like I can improve like basically everything in the body, which is freaking cool. I can improve the number of GLUT4 transporters that we have, okay? So again, if I increase the number of little side doors that I have here, a number of GLUT4 transporters that I have, I'm able to increase my exercise capacity because I'm able to get more sugars in. So therefore I can do more work from an aerobic standpoint or anaerobic standpoint for that matter. I can do more work with those sugars, which means I can work at a higher capacity for a prolonged period of time. So I'm better than the other person because I have better metabolic pathway potential, essentially. Okay, so again, GLUT4 transporters can be upregulated in that way with regular training. Okay, what about fats? Okay, so we've talked about carbohydrate metabolism, how we regulate that, but how do we regulate fat metabolism during exercise? Okay, so we know that lipids or fats are an important fuel source for us during prolonged exercise, also during low intensity exercise. However, we know fat metabolism is slow to be activated, okay? Again, probably around 60 minutes, 45 to 60 minutes, I would say, before we're actually able to metabolize or access fats in a substantial way that would allow us to contribute to metabolism. So effective fat mobilization and oxidation is super important for endurance exercise. Again, if I'm going to do anything greater than 45 to 60 minutes in duration, it would be really neat if I could rely on fats as a fuel source. Okay. So where are we going to get these fats from? Where are we going to get fats from for catabolism? And catabolism is breakdown, okay? So catabolism is to break down. So we can get them from 3 different sources. We can get them, number one, some are free-floating fatty acids in the blood. Probably not very much, though. That's a very small amount. Okay, so number one, some free-floating fatty acids in the blood. Number two is storage within adipose tissue or fat cells, fat tissue. And we have fat tissue pretty much everywhere in the body. Okay, so again, a fat cell will store those fat molecules, obviously, and we can mobilize and use those during prolonged exercise. And then lastly, in the muscle. So intramuscularly, we have fat stored as well. And again, those are probably the easiest for us to mobilize because they're right there, right at the location where we need them. Okay, so where do we get fats from? Some are free floating in the blood, some from adipose tissue, and some from intramuscular or inside the muscle. Okay. A little bit about fat metabolism, and again, we'll finish this up kind of in our next or our final portion of this lecture. But triglycerides are the way, or triglycerides are the molecule that we store as a like a fat molecule. That's the most stable version of fat. So again, triglyceride, I've got this glycerol backbone and 3 fatty acid tails. So here's my glycerol backbone, okay? So basically what I need to do in order to metabolize fats is I need to take this triglyceride out of storage and break it down into a glycerol and free fatty acids. Let's see if I can change my color. I know I'm getting so fancy on you. Okay, so I want to like nip off. So I have a glycerol backbone, and then I have one fatty acid, two fatty acids, three fatty acids, okay? Again, so that's kind of what we want to do out the gate is get them out of storage and break them down into these three fatty acid tails and then that glycerol backbone. Again, increasing the amount of free fatty acids in the blood increases our ability to uptake them at the cellular level, okay? So basically we want to get them out of storage, we're going to put them into the blood, and then therefore we're going to be able to pick those up at the level of the muscle so that we can use them as a fuel. Okay. This process is known as lipolysis. So lipolysis is the breakdown of triglycerides into usable energy, which you know to be ATP. Okay. Rates of lipolysis are dependent on four hormones. Those hormones are epinephrine, norepinephrine, growth hormone, cortisol. There's actually five. I'm a liar. So the rate of lipolysis is dependent on five hormones: epinephrine, norepinephrine, growth hormone, cortisol, and hormone-sensitive lipase, or HSL. Okay, the most important factor is hormone-sensitive lipase. Okay, hormone-sensitive lipase allows us to go to that storage spot and pull out fats out of storage, basically. Okay, so its job is to help to mobilize those fats from their storage bins, basically. Okay, cool thing. We remember how we just talked about that during exercise, I increased the release of epinephrine, norepinephrine, growth hormone, cortisol. Isn't that nice? And they get to help with lipolysis and carbohydrates. Okay, so they're going to help to get sugars in the blood. They're also going to help us to get fats in the blood too, so that we can use either of those fuel sources. Again, we said that with prolonged exercise, the longer I exercise, the more of each of those hormones I'm going to release, which is really neat if I'm interested in continuing on with this exercise bout, and I'm going to need lipolysis. Okay. So how much fats am I going to use, right? So fats may serve as a major fuel source during exercise, but their usage is dependent on three factors. Number one is intensity. Okay, so intensity needs to be moderate or lower in order for me to use fats as a fuel. Duration of exercise is also important. Again, the longer the duration, the higher the percentage of fat usage. Okay, again, we said probably about 45 minutes, maybe up to 60 minutes of exercise before we're even mobilizing fats. So I've got to commit to do 70, 80, 90 minutes at least if I want to get a significant amount of fat burnt in that particular process. And then lastly is the training status, okay? Training status of the individual, okay? Again, I want you to think about this and then I'll explain why. If I'm highly trained, would I prefer to use fats or carbs as a fuel source, okay? And I want you to think about this in terms of the amount that you have stored. Okay, I'm not calling you fat, all right? But I have about 2,000 calories worth of sugar stored. I have about 70,000 calories of fat stored, okay? So I have way more fat stored than carbohydrates stored. I want you to think about this like your parents' bank account, okay? Let's say you have $2,000 in your bank account and they have $70,000 in their bank account, right? Whose money would you rather spend, yours or theirs? Probably theirs, because they have more of it, right? The same is true when we think about energy expenditure, right? I have a limited amount of sugars. I have 2,000 calories of sugars, but I have essentially a limitless supply of fat. I have 70,000 calories in fat. Okay, so I would prefer to use fat. So fat is the preference for a fuel source for individuals that are highly trained. Okay, so the more often I can use fat, the more I can spare or save my glycogen for a higher intensity situation. Okay, so again, three components that are important for us to think about as it relates to how much fat I'm using. Number one is intensity of the exercise. Number two is duration. Longer duration means more fat usage. Intensity needs to be low, moderate in order to use fats. And then training status is number three. So highly trained individuals will tend to use more fats than non-trained individuals. Okay, I think we'll stop there for today. Again, have a great day. There's one more little section for this particular lecture that we will cover in another video.